Assalamualaikum, my name is Ilya Shuhada, and today I will be presenting about second law of thermodynamics. I will be talking about introduction of second law, thermal energy reservoirs, heat engines, and the Carnot heat engines. Okay, we started with introduction to second law of thermodynamics. It is about energy is a conserved property, and no process is known to have taken place in violation of the first law of thermodynamics. A process must satisfy the first law to occur. The satisfying the first law alone does not ensure that the process will actually take place. First, for example, a cup of a hot coffee does not get hotter in a cooler room. A cup of hot coffee left in a cooler room eventually cools off. The process satisfies the first law of thermodynamics since the amount of energy lost by the coffee is equal to the amount gained by the surrounding air. The reverse process, the hot coffee getting even hotter in a cooler room as a result of heat transfer from the room air. We all know that this process never takes place, yet doing so would not violate the first law as long as the amount of energy lost by the air is equal to the amount gained by the coffee. Second example is transferring heat to a wire will not generate electricity. The heating of a room by the passage of electric current through a resistor. Again, the first law dictates that the amount of electric energy supplied to the resistant wire be equal to the amount of energy transferred to the room air as heat. Now, let us attempt to reverse this process. Transferring some heat to the wires does not cause an equivalent amount of electric to be generated in the wires. And the third example is transferring heat to a paddle wheel will not cause to rotate. A paddle wheel mechanism that is operated by the fall of mass. The paddle wheel rotates as the mass falls and stirs a fluid within an insulated container. The potential energy of the mass decreases and the internal energy of the fluid increases, in accordance with the conservation of energy principle. The reverse process, raising the mass by transferring heat from the fluid to the paddle, does not occur in nature, although doing so would not violate the first law of thermodynamics. From those examples, we can conclude that the process proceeds in a certain direction and not in reverse direction. The first law places no restriction on the direction of a process, but satisfying the first law does not ensure that the process can actually occur. The inadequacy of the first law to identify whether a process can take place is remedied by introducing another general principle, which is the second law of thermodynamics. The reverse process discussed above violates the second law of thermodynamics. This violation is easily detected with the help of property called entropy in process cannot occur unless it satisfies both the first and the second law of thermodynamics. The use of the second law of thermodynamics is not limited to identifying the direction of processes. The second law also asserts that energy has quality as well as quantity. The first law is concerned with the quantity of energy and transformation of energy from one form to another with no regard to its quality. And preserving the quality of energy is a major concern to engineers, and the second law provides the necessary means to determine the quality as well as the degree of degradation of energy during a process. As discussed later in this chapter, more of high temperature energy can be converted to work, and thus it has higher quality than the same amount at a lower temperature. The second law defines perfection of thermodynamic processes. It can be used to quantify the level of perfection of a process and point the direction to eliminate imperfection effectively. Next, we will talk about thermal energy reservoirs. In the development of the second law of thermodynamics, it is very convenient to have a hypothetical body with a relatively large thermal energy capacity, mass through specific heat, that can supply or absorb finite amounts without undergoing any change in temperature. Such a body is called a thermal energy reservoir or just a reservoir. Large bodies of water such as ocean, lakes and rivers as well as the atmospheric air can be modeled accurately as thermal energy reservoirs because of their large thermal energy storage capabilities or thermal masses. Likewise, megajoules of waste energy dumped in a large river by power plant do not cause any significant change in the water temperature. The temperature of most furnaces are carefully controlled and they are capable of supplying large quantities of thermal energy as heat in an essentially isothermal manner. Therefore, they can be modeled as reservoirs. Any physical body whose thermal energy capacity is large relative to the amount of energy it supplies or absorbs can be modeled as one. The air in a room, for example, can be treated as a reservoir in the analysis of heat dissipation from a TV set in the room, since the amount of heat transfer from the TV set to the room air is not large enough to have a noticeable effect on the room air temperature. A reservoir that supplies energy in the form of heat is called a source, and one that absorbs energy in the form of heat is called a sink. Thermal energy reservoirs are often referred to as heat reservoirs since they supply or absorb energy in the form of heat. Irresponsible management of waste energy can significantly increase the temperature of portions of the environment, causing what is called thermal pollution. However, by careful design and management, the waste of energy dumped into a large body of water can be used to improve the quality of marine life by keeping the local temperature increase within safe and desirable levels. So this is about this of relatively large thermal masses can be modeled as a thermal energy reservoirs. And this is some figure of source of supplies energy in the form of heat. It sinks and absorbs. Next, we talk about heat engines. Work can be easily converted to other forms of energy, but converting other forms of energy to work is not that easy. The mechanical work done by the shaft first converted to the internal energy of the water. This energy may then leave the water as heat. We know from experience that any attempt to reverse the process will fail. That is, transferring heat to the water does not cause the shaft to rotate. From this and other observation, we conclude that work can be converted to heat directly and completely. But converting heat to work requires the use of some special device. These devices are called heat engines. Okay, characterized heat engines are first receive heat from high temperature source, and then we convert part of this heat to work, usually in the form of a rotating shaft. The third one, they reject the remaining waste heat to a low temperature sink, and then they operate on a cycle. This is the figure of heat engines and other cyclic devices usually involve a fluid to and from which heat is transferred while undergoing a cycle. This fluid is called the working fluid. Engines that involve internal combustion, such as gas turbines and car engines, fall into this category. These devices operate in a mechanical cycle, but not in a thermodynamic cycle. Since the working fluid, the combustion gases, does not undergo a complete cycle. Instead of being cooled to the initial temperature, the exhaust gases are purged and replaced by fresh air and fuel mixture at the end of the cycle. So some of terms that we have to know is in amount of heat supplied to the steam in a boiler from high temperature, and then the out amount of heat rejected from the steam in condenser to a low temperature sink, and then the work out amount of work delivered by the steam as it expands in turbine, and then the work in is amount of work required to compress water to boil pressure. The net work output of this power plant is simply the difference between the total work output of the plant and the total work input. This is the general equation, and then the net work output of the system is also equal to the net heat transfer to the system. And the equation. Thermal efficiency. First, for heat engines, the desired output is the net work output, and the required input is the amount of heat supplied to the working fluid. Thermal efficiency is equal to net work output divided by total heat output. Second, to bring uniformity to the treatment of heat engines, refrigerator, and heat pumps, we define these two quantities, which is QH, magnitude of heat transfer between the cyclic device and the high temperature medium at temperature, and then the QL is magnitude of heat transfer between the cyclic device and the low temperature medium at temperature. The network output of thermal efficiency relation for any heat engines is W net and out equals to QH minus QL. And this is a Kelvin-Planck statement. The heat engine cycle shown in this figure, even under ideal condition, a heat engine must reject some heat to a low temperature reservoirs in order to complete the cycle. No heat engine can convert all the heat it receives to useful work. This limitation on the thermal efficiency of heat engines forms is the basis for Kelvin-Planck statement of the second law of thermodynamics, which is expressed as follows. It is impossible for any devices that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. A heat engine must exchange heat with a low temperature sink as well as high temperature source to keep operating. The Kelvin-Planck statement can also be expressed as no heat engine can have a thermal efficiency and 100% or as for a power plant to operate. The working fluid must exchange heat with the environment as well as the furnace. The impossibility of having a 100% efficient heat engine is not due to friction or other dissipative effect. It is a limitation that applies to both the idealized and the actual heat engines. So this is the heat engines that violates the Kelvin-Planck statement of the second law.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Ain. My metric number is TH19021, and today I'm going to talk about refrigerators and heat pumps. We all know from experience that heat is transferred in the direction of decreasing temperature, that is, from high temperature mediums to low temperature ones. This heat transfer process occurs in nature without requiring any devices. The reverse process, however, cannot occur by itself. The transfer of heat from a low temperature medium to a high temperature one requires special devices called refrigerators. Refrigerators, like heat engines, are cyclic devices. The working fluid used in the refrigeration cycle is called a refrigerant. The most frequently used refrigeration cycle is the vapor compression refrigeration cycle, which involves four main components: a compressor, a condenser, an expansion valve, and an evaporator. The refrigerant enters the compressor as a vapor and is compressed to the condenser pressure. It leaves the compressor at a relatively high temperature and cools down the condensers as it flows through the coils of the condenser by rejecting heat to the surrounding medium. It then enters a capillary tube. When its pressure and temperature drop drastically due to the throttling effect, the low temperature refrigerant then enters the evaporator, where it evaporates by absorbing heat from the refrigerated space. The cycle is completed as the refrigerant leaves the evaporator and re-enters the compressor. Coefficient of performance. The objective of a refrigerator is to remove heat from a refrigerated space. Requires of a work input of W net in. COPR equals to desired output over required input. Conservation of energy principle for cyclic devices is QH minus QL, then becomes COPR equals to QL over QH minus QL equals to 1 over QH over QL minus 1. COPR can be greater than unity. The amount of heat removed from the refrigerated space can be greater than the amount of work input. The coefficient of performance is the desire to avoid the oddity of having efficiencies greater than unity. Heat pumps. Another device that transfers heat from a low temperature medium to a high temperature one is the heat pump. Refrigerators and heat pumps operate on the same cycle but differ in their objective. The objective of a refrigerator is to maintain the refrigerated space at a low temperature by removing heat from it. Discharging this heat to a higher temperature medium is merely a necessary part of the operation, not the purpose. The objective of a heat pump, however, is to maintain a heated space at a high temperature. This is accomplished by absorbing heat from a low temperature source such as well water or cold outside air in winter and supplying this heat to a high medium such as a house. An ordinary refrigerator that is placed in the window of a house with its door open to the cold outside air in winter will function as a heat pump, since it will try to cool the outside by absorbing heat from it and rejecting this heat into the house through the coils behind it. Coefficient of performance COP heat pump equals to desired output over required output, or COP heat pump equals to QH over QH minus QL. Comparison of equation coefficient of performance for refrigerators, we found COP heat pump equals to COP refrigerators plus 1. Implies that COP heat pump is always greater than unity since COP refrigerator is a positive quantity. Function as a resistance heater by supplying as much energy to the house as it consumes. In reality, part of QH is lost to the outside air through piping and other devices, and coefficient of performance heat pump may drop below unity when the temperature is too low. Heat pumps that use the cold outside air referred as air source heat pumps. Heat pumps that use the ground as the heat source are called geothermal heat pumps or ground source heat pumps. Air conditioners can be used as a heat pump in winter by installing it backwards. Air conditioning systems that equipped with proper control and reversing valve operate as air conditioners in summer and heat pumps in winter. Performance of refrigerators and air conditioners and heat pumps. Seasonal energy efficiency ratio (EER) is the ratio of the total amount of heat removed by an air conditioner or heat pump during a normal cooling session in BTU to the total amount of electricity consumed in watt hours, and it is a measure of seasonal performance of cooling equipment. Energy efficiency ratio (EER) is a measure of instantaneous energy efficiency and is defined as the ratio of the rate of heat removal from a cooled space by the cooling equipment to the rate of electricity consumption in steady operation, both unit in BTW over watt hour. 1 kilowatt hour equals to 3412 BTU. 1 watt hour equals to 3.412 BTU. A device that removes 1 kilowatt hour of heat from the cooled space for each kilowatt hour of electricity it consumes, COP equals to 1, will have an EER of 3.412, which means EER equals to 3.412, the coefficient of performance refrigerator. Promote the efficient use of energy. Air conditioner or heat pumps have SEER value from 13 to 21, corresponding to COP values 3.8 to 6.2. Best performance is achieved using units equipped with variable speeds drives, also called inverters. Variable speed compressor and fan allow the unit to operate at maximum efficiency for varying cooling heating needs and weather conditions. EER or COP of a refrigerator decreases with decreasing refrigeration temperature. COPs of refrigerators in the range of 2.6 to 3.0 for cutting and preparation room, 2.3 to 6.6 for meat, deli, dairy, and produce, 1.2 to 1.5 for frozen foods, and 1.0 to 1.2 for ice cream units. It is good energy conservation practice to use separate refrigeration systems to meet different refrigeration needs. The second law of thermodynamics, Clausius statement. It is impossible to construct a device that operates in a cycle and produce no effect other than the transfer of heat from a lower temperature body to a higher temperature body. It is simply stated that a refrigerator cannot operate unless its compressor is driven by an external power source such as electric motor. The net effect of the surroundings involves the consumption of some energy in the form of work to the transfer of heat from a colder body to a warmer one, leaves a trace in surroundings and comply with the statement of the second law. Equivalence of two statements. Any device that violates the Kelvin-Planck statement also violates the Clausius statement and vice versa. The heat engine is assumed to have, in violation of the Kelvin-Planck statement, a thermal efficiency of 100%, and therefore it converts all the heat it receives to work. This work is now supplied to a refrigerator that removes heat in the amount of QL from the low temperature reservoir and rejects it in the amount of QH plus QL to high temperature reservoir. During this process, the high temperature reservoir receives a net amount of heat QL, the difference between QH plus QL and QH. Thus, the combination of these two devices that transfer heat in an amount of QL from a cooler body to a warmer one without requiring any input from outside. It is clearly a violation of the Clausius statement. Therefore, a violation of the Kelvin-Planck statement results in the violation of Clausius statement. 6.5. Perpetual motion machine. Perpetual motion machine 1 violates first law by creating energy. Perpetual motion machine 2 violates second law. Claims that once the system is started, this power plant will produce electricity indefinitely without requiring any energy input from the outside. The system enclosed by the shaded area is continuously supplying energy to the outside at a rate of Q out plus W net out without receiving any energy. This system is creating energy at a rate of Q out plus W net out. Violate the first law. All the heat transferred to the system in the boiler will be converted to work. However, some heat losses and friction between the moving components are unavoidable, and that these effects will reduce the efficiency somewhat. Works on a cycle and does a net amount of work while exchanging heat with a single reservoirs only. Satisfy the first law but violates the second law. 6.6. Reversible and irreversible process. Second law of thermodynamics states that no heat engine can have an efficiency of 100%. Reversible process. Defined as a process that can be reversed without leaving any stress on the surrounding. Both the system and the surroundings are returned to their initial states at the end of the reverse process. Net heat and net work exchange between the system and the surroundings is zero from the original and reverse process. Do not occur in nature. Work-producing devices such as car engines and steam turbines deliver the most work. Work consumption devices such as compressors and pumps consume the least work. The better the design, the lower the irreversibilities, and the higher the second law efficiency. Irreversibilities include friction, unrestrained expansion, mixing of two fluids, heat transfer across a finite temperature difference, electric resistance, inelastic deformation of solids, and chemical reaction. One of the examples is friction. Friction is a familiar form of irreversibility associated with bodies in motion. When two bodies in contact forced to move in relative to each other, a friction that opposes the motion develops at a the interface of these two bodies, and some work is needed to overcome this force. The energy supplied as work is eventually converted to heat during the process and is transferred to the bodies in contact, as evidenced by a temperature rise at the interface. When the direction of the motion is reversed, the body restored to the original state, but the interface does not cool and heat is not converted back to work. The larger the friction forces involved, the more irreversible the process is. The second example is unrestrained expansion of a gas. When the membrane is ruptured, the gas fills the entire tank. To restore the system to its original state is to compress to its initial volume while transferring heat from the gas until it reaches its initial temperature. Based on conservation of energy, the amount of heat transferred from the gas equals the amount of work done on the gas by the surroundings. The restoration of the surroundings involves conversion of this heat completely to work, which would violate the second law. Internally and externally reversible process. A process is called internally reversible if no irreversibility occurs within the boundaries of the system during the process. A system proceeds through a series of equilibrium states, and when the process is reversed, the system passes through exactly the same equilibrium states when returning to its initial state. The quasi-equilibrium process is an example of an internally reversible process. A process is called externally reversible if no irreversibilities occur outside the system boundary during the process. Heat transfer between a reservoir and a system is an externally reversible process if the outer surface of the system is at the temperature of the reservoir. A process is called totally reversible or simply reversible if it involves no irreversibilities within the system or its surrounding. A totally reversible process involves no heat transfer through a finite temperature difference, no non-quasi-equilibrium changes, and no friction or other dissipative effects.
Good day everyone. My name is Nufazihan binti Arifan. My metro ID is TH19029. I'm going to explain about second law of thermodynamics regarding to the subtopic 6.7, 6.8, 6.9 and a little bit of 6.11. Okay, so we're gonna start. I'm gonna start my presentation with second law of thermodynamics. So first of all, we're gonna look at 6.7, the Carnot cycle. Okay, so the Carnot cycle, it is the performance of a series of heat engines depends significantly on how the individual processes that make up the cycle are conducted. The network, hence the cycle efficiency, can be maximized by using processes that require the least amount of work and produce the most, which is by using reversible processes. So it is no surprise that reversible cycles are the most effective cycles, since it is cycles that consist entirely of reversible processes. Okay, the Carnot cycle was initially suggested by French engineer, which is Sadi Carnot, in 1824. The Carnot heat engine is called the theoretical heat engine, which operates on the Carnot cycle. The Carnot cycle consists of 4 reversible processes, which is 2 isothermal processes and 2 adiabatic processes, and can be performed in either a closed or a steady flow system. Okay, so this is the example of Carnot cycle, the execution of the Carnot cycle in a closed system. Okay, consider a closed system created by a gas trapped in an adiabatic piston, which is the cylinder apparatus as shown in this figure. The cylinder isolation head is such that the head can be removed to touch as heat transfer reservoirs. Okay, and then we're going to look through 4 reversible process of Carnot cycle. Okay, the first one is reversible adiabatic expansions, which is from process 2-3. Okay, at state 2, the reservoir head that approach the cylinder head is removed and the insulation replaced so that the machine turns adiabatic. Okay, and then the second one is the reversible isothermal expansion. The fuel temperature is TH and the cylinder head is in close proximity contact with TH temperature source. The gas is allowed to spread gradually doing surrounding work. When the gas expands, the gas temperature begins to go down. Okay, the amount of total heat transferred to the gas during this process is called QH. And the third one is the reversible adiabatic compression, which is at process 4 to 1. Okay, the state 4 is such that where the reservoir is low temperature being removed, the insulation on the cylinder head and the gas is placed back, is reversibly compressed, and the gas returns to its initial state, which is state 1. Okay, and the last one is reversible isothermal compression, which is for process 3 to 4. Okay, the cylinder head insulation is removed and the cylinder is brought into contact at TL temperature with the bath. So an external force forces the piston inwards, performing research on the air. As the gas is compressed, it begins to increase in temperature. Okay, so it keeps on going until the piston enters state 4. Okay, this is the example of the PV diagram for the Carnot cycle. Okay, and this is the reverse Carnot cycle. It can reverse all the processes that comprise it, in which case it becomes the Carnot refrigeration cycle. This time the cycle remains exactly the same, except that the direction of any heat and work interactions are reversed. Heat in the quantity of QL is absorbed from the low temperature reservoir. Heat in the quantity of QH is rejected into a high temperature reservoir. Okay, this is the example of PV diagram for the reverse Carnot cycle. Okay, and then we're going to look through 6.8, the Carnot principle. Okay, the conclusions pertain to the thermal efficiency of reversible and irreversible heat engines, and they are known as the Carnot principles, expressed as the following, which is number one is the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same two reservoirs. And then the second one is the efficiencies of a reversible heat engines operating between the same two reservoirs are the same. This is the figure of the Carnot cycle, the Carnot cycle principle. Okay, this is the example of the proof for the first Carnot principle. Okay, and then we're going to look through 6.9, the thermodynamics temperature scale. Since energy reservoirs are characterized by their temperatures, the thermal efficiency of reversible heat engines is a function of that reservoir temperatures only. That is, this is the formula for the thermodynamics temperature scale. And based on this figure, it is the arrangement of heat engines used to develop the thermodynamic temperature scale. And this is the formula we got from the step and the process. Okay, and for figure 643, for reversible cycles, the heat transfer ratio is QH over QL can be replaced by the absolute temperature ratio, which is TH over TL, based on the equation beside.
And this is next is the Carnot heat engine. The hypothetical heat engine that operates on the reversible Carnot cycle is called the Carnot heat engine. The thermal efficiency of any heat engine, reversible or irreversible, is given by equation. This is H thermal 1 minus QL over QH. This is the equation 1, where QH is a transfer heat to heat engine from high temperature reservoirs at TH, and the QL is heat rejected to a low temperature reservoirs. The efficiency of Carnot heat engine or any reversible heat engine becomes like this equation. It's actually the same, but we change the Q to T because the efficiency. An actual heat engine cannot reach this maximum theoretical efficiency value because it is impossible to completely eliminate all the irreversibilities associated with the actual cycle. Note that TL and TH in equation 1 are absolute temperature. Using 8 degrees Celsius or 8 Fahrenheit for temperature in this relation give result grossly in error. It is obvious from equation 1 that the efficiency of Carnot heat engine increases as the TH is increased or as TL is decreased. This is to be expected since as TL is decreases, so does the amount of heat rejected, and as the TL approaches zero, the Carnot efficiency approaches unity. Thank you.
And then we're going to look through 6.11, the Carnot refrigerator and heat pump. A refrigerator or a heat pump that operates on the reverse Carnot cycle is called a Carnot refrigerator or a Carnot heat pump. The coefficient of performance of any refrigerator or heat pump, reversible or irreversible, is given by this equation. Okay, and then the coefficients of performance of actual and reversible refrigerators operating between the same temperature limits can be compared as follows. Okay, I got this. This is the references. References are from Yunus H. Ngel, Thermodynamics 8th edition. So we can look through that. Okay, this is also the current refrigerator and heat pump. Okay, so that's all from me.
Example
Thank you.
6.8 Malfunction of refrigerator light switch. The interior lighting of a refrigerator is provided by incandescent lamps whose switches are actuated by the opening of the refrigerator door. Consider a refrigerator whose 40-watt light bulb remains on continuously as a result of a malfunction of the switch. If the refrigerator has a coefficient of performance of 1.3 and the cost of electricity is 12 cents per kilowatt hour, determine the increase in the energy consumption of the refrigerator and its cost per year if the switch is not fixed. Solution: the light bulb of the refrigerator malfunctions and remains on. The increase in electricity consumption and cost are to be determined. Assumptions: the life of the light bulb is more than 1 year. Analysis: the light bulb consumes 40 watt of power when it is on and thus adds 40 watt to the heat load of the refrigerator. Noting that COP of the refrigerator is 1.3. The power consumed by the refrigerator to remove the heat generated by light bulb is W refrigerator equals to Q refrigerator over COP refrigerator equals to 40 watt over 1.3 will get 30.8 watt. Therefore, the total additional power consumed by the refrigerator is W light plus W refrigerator equals to 40 watt plus 30.8. You will get 70.8 watt. The total number of hours in a year is annual hours equals to 365 days per year times 24 hours per day equals to 8,760 hours per year. Assuming the refrigerator is open 20 times a day for an average of 30 seconds, the light would normally be on for normal operating hours equals to 20 times per day times 30 seconds per time times 1 hour per 3,600 seconds times 365 days per year. You will get 61 hours per year. Then the additional hours the light remains on as a result of the malfunction becomes additional operating hours equals to annual hours minus normal operating hours, which is 8,760 minus 61, you get 8,699 hours per year. Therefore, the additional electric power consumption and its cost per year are additional power consumption equals to W total additional times additional operating hours, which is 0.0708 kilowatt times 8,699 hours per year. You will get 616 kilowatt hour per year. And additional power cost, which is additional power consumption times unit cost, 616 kilowatt hour per year times $0.12 per kilowatt hour, you will get $73.9 per year. Discussion: note that not repairing the switch will cost the homeowner about $75 a year. This is alarming when we consider that at 0.2 cent per kilowatt hour, a typical refrigerator consumes about $100 worth of electricity a year. Summary: the second law of thermodynamics states that processes occur in a certain direction, not in any direction, and does not occur unless it satisfies Bohr's law. Bodies that can absorb or reject finite amounts of heat isothermally are called thermal energy reservoirs or heat reservoirs. Work can be converted to heat directly, but heat can be converted to work only by some devices called heat engines. Thermal efficiency of a heat engine is defined as W net output over QH equals to 1 minus QL over QH. Refrigerators and heat pumps are devices that absorb heat from low temperature media and reject it to higher temperature one. The performance of refrigerator or heat pump is expressed in terms of the coefficient of performance. Sorry, I should not do this.